Welcome to qnawire.
And then we're asked to use this information to calculate the density of the charge carriers and the Fermi energy of sodium. So starting with the density of charge carriers, which I will denote here as N subscript E because it's the electron density. Well, dimensionally, we want this to be per unit volume. So we're going to want this to be a per unit volume measurement. And as such, we know it will be something along the lines of, well, if just a common relation of mass is equal to density times volume. To get v to the minus 1, we'd have to do our density divided by the mass. So in order to get this value as a per unit volume, just given the dimensions that we've got, we can say that our density of charge carriers Ne will be something along the lines of, well, we'll need density over mass. So that will be our density here, and then it will be over our mass. However, we know that sodium, we're told in the question, that it is monovalent. And what that means is that it contributes 1 electron per atom to our conduction band. So it means that we will have to multiply this fraction by the Avogadro constant Na. Now the Avogadro constant relates the number of molecules or atoms, or in this case charge carriers, in the sample with the amount of substance in that sample. So we have number of atoms being analogous to number of electrons in the sample because of this monovalency of sodium. So subbing in some values, we have our density already, that is 0.971 grams per centimeter cubed. Multiplied by our Avogadro number, which is, you can find anywhere as 6.02 times 10 to the 23, with units of per mole. And that will be over our atomic mass, which is, sorry, our molar mass, which is 23.0 grams per mole. And the reason I've kept these units in is because we've got a lot of different non-SI units flying around here, so we need to just make sure that we get our answer into SI units at the end, so it just avoids us making a mistake by not writing down the units here. And that comes out as 2.54 times 10 to the 22. And so our units will be, well, cancelling everything down, that comes out as number of charge carriers per centimeter cubed. And now we need to convert this value into SI units. Well, 1 centimeter to the minus 3 is going to be 10 to the 6 meters to the minus 3. So therefore, our charge carrier density in SI units will be 2.54 times 10, multiplying by 10 to the 6 gives us 10 to the 28 meters to the minus 3. So this part of the question then asks us to work out the Fermi energy EF, which is just simply the highest occupied energy state available at 0 Kelvin. So according to the free electron theory of metals, and now I'm not going to go into the derivation here because the question simply wants us to use this relationship, our Fermi energy is given by Planck's constant h over 2 times by our mass of the electron, me, multiplied by 3 times by our charge carrier density that we worked out in the previous question, ne, over 8 pi, all to the power of 2/3, and making sure that we square our h bar there. So plugging in some numbers, we have h bar, which is in SI units 6.63 times 10 to the minus 34 joule seconds, all squared, over 2 times by our electron mass, which is 9.11 times by 10 to the minus 31 kilograms. And then open bracket, we have 3 multiplied by our electron charge carrier density, which we worked out to be 2.54 times 10 to the 28 meters to the minus 3. And that's over 8 pi. All to the power of 2/3. And this will come out as about 5.054 times 10 to the minus 19 joules. Now, converting to electron volts, because that is a more, useful measurement of energy at the atomic level. So we want to divide by our elementary charge, which is 1.6 times 10 to the minus 19 coulombs, giving us a value of 3.16 electron volts.